Hi everyone, my name is Rahul. I work as a senior applied research scientist, and in this video we'll go over a very interesting topic known to us as speculative decoding. Now, speculative decoding, you must have heard of that or maybe not, but we'll cover that in this lecture. So just to provide some context, often when we are using large language models, due to the nature of these models being large and having billions and even trillions of parameters these days, we need to have a lot of optimization approaches to serve the real-time use cases. Why? Because if you're talking about a real-time use case, if your model takes forever to respond, it just deteriorates the user experience and it defeats the purpose. So what are some of the ways in which we can optimize a model? So there are multiple ways. Some of you might have heard about distillation or model pruning. Then there's quantization. There is something known to us as KV cache optimization. We'll cover that in some other video maybe. Then there's mixture of experts. There are a lot of things that can be done. And in the realm of those things lies speculative decoding. Now, it's one of the most popular methods, and although GPT-4 and the OpenAI models haven't quite revealed their structure and how the architecture looks like under the hood, but then I'm sure that it is one of the most popular methods that they might be using under the hood, that they most likely might be using under the hood. So let's cover speculative decoding in this video. So we'll be covering a very intuitive explanation of speculative decoding because there is an entire research paper that you can read if you are interested to learn more about this. But optimization as a subject, particularly in the case of large language models, is becoming very popular because LLMs as a whole have really become commoditized these days. And to truly stand out and know more about LLMs, it is very important to touch on the topic and not only just touch upon that, maybe dive deep into the topic of optimization and what are the different ways in which people are trying to optimize the inference of these LLMs because it's a highly growing topic and there is a lot of research around this. So let's start with the very fundamental question. The first question might be like why LLMs need optimization. So if we talk about LLMs like GPT-4, they are quite powerful but can be slow and computationally expensive during inference. I have highlighted the word can, and why? Because if we interact with the OpenAI model like let's say GPT-4, we have observed that they are blazing fast enough and they generate response pretty quick, right? So one of the things that might be going behind the scenes is speculative decoding. Like I mentioned, there is a lot other things that people can do to make the LLM inference faster, but yeah, that's the fundamental problem. And why does it happen? Like why these models are slow in the first place? Because if you consider the transformer decoder architecture, they generate the text one token at a time, and that's what we call it as auto-regressive decoding. So there are two categories of large language models. First one is the auto-encoding models, and the second type of models are the auto-regressive models. So all the generational models that you see for text generation are mostly based on the auto-regressive kind of architecture. And then to address this and solve for the latency for the real-time use cases, let's say like things like chatbot and enterprise AI systems and then real-time applications, researchers from Google and DeepMind came up with this thing called as speculative decoding. And typically what happens during inference is that each new token depends on all the previously generated tokens, making text generation sequential and a slow process. So essentially what you're trying to model at the time of generation is the probability of a token appearing, let's say, let's call it WT at time T, considering all the previous tokens. So given W1, W2 and all the tokens up till that particular point. So an example could be, let's say that the prompt that we have is the capital of France is, and then there is a hyphen. So that's what the model needs to predict. Now the model's next token prediction would highly likely be Paris, but it can only generate that token after processing the entire input sequence. And that is a major problem because all of this makes it pretty sequential and that would make it very slow. So then once it generates the token Paris, it will probably generate the next token that would be a full stop and the sentence will be completed. So this one at a time approach makes the inference slow and time consuming. And one of the ways to solve for that is through speculative decoding. Now let's talk about what happens exactly in the speculative decoding phase, right? So speculative decoding speeds up this process by using two models instead of one. So the first model is often known to us as the draft model, which is often a slower model, but it's designed to be fast. And what it does, it quickly predicts multiple tokens at once. And then we have the main model, which is our large language model or the larger model in this case, which is designed to be more accurate and better in terms of performance and the quality of generation. So the main model verifies and corrects the mistake from the draft model if needed. So if you want to think of an example, think of it like this. If you have a llama series of models, the draft model or the smaller model could be, let's say, a llama 3b, or let's say even a llama 70b. So how you can pick up this draft model, it could be a distilled version of the larger model that you're trying to train, or it could be any transformer based model as long as it is fast. So instead of generating one token at a time, we now generate a batch of tokens in parallel, which is significantly improving the efficiency. So the draft model will generate multiple tokens in parallel, making the predictions really quick. And then the main model would verify these tokens, accepting the correct ones and then regenerating the more complex or incorrect ones as needed. And this allows easy to predict tokens to be processed faster while ensuring the overall accuracy. So instead of generating one token at a time, we are now generating a batch of tokens in parallel, and that is helping up a lot. So how does this work? So the draft model first predicts a set of tokens. So let's say if we take the original example, the capital of France is, so the output of the draft model could be something like this. It could generate a bunch of tokens. Let's say it completes and generates these tokens, Paris, and it is beautiful. So the entire sentence could be, let's say the capital of France is Paris and it is beautiful. That's what the draft model would generate, the tokens highlighted in red. And then the main model can verify these predictions. So it can go token by token. So it can take each token to determine if it agrees with that or not. And obviously, when I say each token, so it's pretty obvious that we can parallelize these tasks and look at these tokens in parallel. So the first token in this case could be, let's say, Paris. So let's say the model tries to evaluate this token Paris. So the capital of France is Paris. It looks good to the model, so it kind of accepts that, the main model. And then the second token is, let's say, and. So the capital of France is, and if an and occurs after that, so it's kind of an incorrect word, and that's where the main model will reject everything after that and word, and it will recompute from that particular point onwards, right? So the main model will then generate the remaining tokens. So when and was rejected, the main model generates the correct continuation of the sequence. That will be a full stop. And finally, we'll end up with something like the capital of France is Paris, full stop. So how does the draft model decide which tokens to generate? That's a very important question, right? Because the draft model is trained as a smaller version of the main model like we discussed. It could be either a distilled model or a smaller transformer based model optimized for speed. And the draft model generates the tokens following the standard autoregressive probability distribution, that it tries to model the probability of a token or a word appearing at time t given all the previous tokens prior to that, and that's what this says. And it tries to prioritize speed over deep reasoning. So what it tries to do is basically it tries to approximate the best tokens possible given an input prompt. And then it sometimes might make errors, like we said, it is trying to approximate, so it might make errors, but that's okay because the main model can correct those errors looking at the tokens that it generates. So to summarize, what we can understand here is that the first step would be to generate a speculative sequence S of length k, and therefore the name speculative decoding, because as you can see that the draft model in this case is trying to speculate a bunch of tokens given an input prompt. So we have a series S of tokens, let's say WT plus 1, WT plus 2, all the way up till WT plus K, where each of these WIs is belonging to or is sampled from the P draft of W, that is basically the probability of the token coming in from the draft model. Once you generate these sequences, the second step is the main model will check for each of the tokens in parallel. So if the P main of W, that is the probability that the token came from the main model or the larger model, if the P main of W is high for every token belonging from S, the token is basically accepted, else the main model will reject the token and it would recompute from that particular point where it rejected the particular token. And finally, the final sequence construction would be a sum of your accepted draft tokens, that is the tokens which were generated by the draft model and accepted by the main model, plus the recomputed tokens. And by doing this batch verification of tokens in parallel, speculative decoding reduces the latency by a significant margin without compromising on the accuracy. And that's how this entire thing works. This is a very simple and intuitive explanation. Like I mentioned, there is an entire research paper on this particular subject, so feel free to check that out. And definitely there are a lot of other optimization hacks that could be tried when it comes to LLM based inference. So definitely I do plan on covering those as well. And hopefully you learned something new. Maybe you heard of this term speculative decoding, or maybe you hadn't heard of this before, but now you know at least a basic understanding of what happens under the hood. There are other details that I mentioned could be referred to from the research paper, but yeah, hopefully it gave you a good insight about how this thing works internally. And once again, this could be an important interview question, because like I mentioned that optimizations on the LLM inference side is becoming a hot topic these days, and a lot of research is going around that. So if you are applying for a Gen AI role and you want to stand out from the candidates, you need to spend time on optimization and learn how the LLM inference is being optimized. So hopefully this video was a good starting point in that direction. And if you like this video, please encourage by liking this particular video and subscribe to this channel for more such content around Gen AI, classical machine learning, and interview prep in general around data science. So I'll see you in the next video then. Until then, stay safe, take care, and see you in the next video then. Bye bye.